Look up at the night sky. What do you see? Pinpricks of light, distant stars, maybe a planet or two. But what you're actually looking at is only the tiniest fraction of what's truly out there. Most of our universe is quite literally invisible. Dark matter, hidden galaxies, cosmic structures so vast they bend the very fabric of space and time. All of it exists beyond what our eyes, or even our most powerful telescopes, can perceive. But what if I told you there's a natural phenomenon, a kind of cosmic magic trick, that lets us glimpse into that unseen realm? A phenomenon that acts as nature's own ultimate telescope, revealing secrets we once thought were forever locked away. This isn't science fiction, it's gravitational lensing, one of the most extraordinary tools in modern astronomy. It works like this. Imagine space as a stretched out sheet, and when you place a massive object like a galaxy or a black hole on it, it creates a dip, a curvature. Now, when light from objects behind that massive object travels toward us, it follows that curve, bending around it like a lens. That distortion magnifies and warps the light, sometimes even creating multiple images or brilliant arcs of distant galaxies we would otherwise never see. It's as if the universe itself is handing us a key to unlock its deepest mysteries, and what we're discovering with this key is nothing short of breathtaking. Gravitational lensing allows us to map dark matter, the invisible scaffolding of the cosmos, observe some of the earliest galaxies ever formed, and even test the very laws of physics under conditions we could never replicate here on Earth. It's reshaping our understanding of reality, offering clues about the nature of time, the expansion of the universe, and the fate of everything we know. In this video, we're going to journey together into how this incredible cosmic phenomenon works, what it's revealing to us right now, and how it might just revolutionize not only space exploration but our very place in the cosmos. Strap in, we're about to see the unseeable. To understand how this cosmic lens works, we need to go back to a revolutionary idea from over a century ago. In 1915, Albert Einstein presented his theory of general relativity, which completely redefined our concept of gravity. Before Einstein, we thought of gravity as a simple force of attraction between masses as described by Isaac Newton. Einstein's genius was in realizing that gravity isn't really a force in the traditional sense at all. Instead, he proposed that mass and energy actually warp the very fabric of the universe itself, the four-dimensional continuum we call spacetime. Think of spacetime as a giant, flexible trampoline mat. Now place a heavy bowling ball in the center. What happens? The mat stretches and curves downward, creating a deep well around the bowling ball. If you then roll a few marbles across the trampoline, they won't travel in straight lines. Instead, they'll spiral inward, following the curves created by the heavy object. In this analogy, the bowling ball is a massive star or galaxy, and the marbles are beams of light traveling through the universe. The light isn't being pulled by a force, it's simply following the shortest path along the curved geometry of spacetime. This warping effect is the engine behind gravitational lensing. When the light from an incredibly distant galaxy travels across the cosmos for billions of years toward our telescopes, its path is never perfectly straight. If that light passes near a massive object like a cluster of galaxies, on its way to us, it will dip into and travel along the curvature of spacetime that this cluster creates. This bends the light's trajectory, much like how a glass lens bends light to focus it. The more massive the object, the deeper the warp in spacetime, and the more dramatic the bending of light. You can see a simple version of this effect yourself. Take a look through the bottom of a wine glass. The curved glass distorts and warps whatever is behind it, sometimes even creating multiple stretched images. Or consider a water droplet on a window. The droplet acts as a tiny lens, magnifying and bending the view of the world outside. A gravitational lens does the exact same thing, but on a truly cosmic scale. It can magnify faint, faraway galaxies, making them appear brighter and larger to our telescopes. It can also smudge their light into long, faint arcs, like celestial smiley faces in the sky, or even split a single distant quasar into 4 or 5 identical copies. This isn't just a theoretical prediction, it's an observable fact that has been confirmed time and again. During a solar eclipse in 1919, scientists observed that the light from stars near the sun was slightly bent, causing their positions in the sky to appear shifted exactly as Einstein's equations had forecast. Today, we see this phenomenon everywhere we look in the deep field images from telescopes like Hubble and James Webb. These natural telescopes are allowing us to peer further back in time than ever before, turning the invisible universe into a map we can finally begin to read. It's one thing to have a brilliant theoretical prediction, and another to actually see it confirmed in the heavens. For a long time, even Einstein himself was skeptical that we would ever observe the most dramatic effects of gravitational lensing. He thought the alignment needed between a distant light source and a massive foreground object would be so precise, so astronomically unlikely, that it was probably impossible to detect. In a 1936 paper, he essentially wrote it off as a curious but unobservable phenomenon. But the universe, as it often does, had a surprise in store. The first major breakthrough came in 1979. Astronomers were studying an object known as twin quasars, two incredibly bright, star-like points of light that were suspiciously close together and identical in every way. Quasars are among the most luminous objects in the universe, powered by supermassive black holes at the hearts of distant galaxies. So finding two that were exact twins right next to each other seemed too strange to be a coincidence. The revelation was breathtaking. They weren't two separate objects at all. They were two separate images of the very same quasar. Its light, on its billion-year journey to Earth, had been split in two by the gravitational field of an entire galaxy sitting directly between it and us. This was the first confirmed gravitational lens, and it was a resounding validation of Einstein's century-old theory. But the real cosmic magic trick, the most beautiful and conclusive evidence, is something called an Einstein ring. This occurs when the alignment is absolutely perfect. The distant light source, the massive foreground lens like a large galaxy cluster, and our telescope all line up in a perfectly straight line. When this happens, the gravity of the foreground object bends the light from the background object so uniformly that it gets smeared into a complete circle of light around the lens. It's a perfect halo, a ring of fire forged by gravity itself. Seeing the first Einstein rings was a watershed moment for astronomy. It wasn't just a confirmation of a complex theory, it was a demonstration of a powerful new tool. Suddenly, we had a way to use these natural telescopes scattered across the cosmos. A single massive galaxy cluster could act as a lens, magnifying the incredibly faint light from galaxies so far away they existed when the universe was just an infant. This opened a window into the deepest reaches of space and time, allowing us to observe the formation of the first galaxies in a way we never thought possible. That first discovery in '79 didn't just prove Einstein right. It handed us the key to a much larger, much older, and far more mysterious universe than we had ever imagined. So what creates these massive curves in space-time powerful enough to perform such feats? The universe provides its own set of ultra-powerful lenses, primarily in the form of galaxy clusters. These are the true heavyweights of the cosmos, not just single galaxies but immense gatherings of hundreds or even thousands of them, all bound together by gravity. Add to that the vast clouds of hot gas and, most importantly, the enormous halos of invisible dark matter that make up most of their mass, and you have an object so tremendously massive that it warps spacetime into a profound natural lens. The combined gravity of a cluster like this doesn't just bend light slightly. It creates a powerful optical effect that can magnify the galaxies behind it by 10, 50, or even 100 times. This magnification is our golden ticket to the early universe. Think of it like this. Even our most advanced telescopes, like the James Webb, have a fundamental limit to how far they can see. The most ancient galaxies are incredibly faint, their light stretched into the infrared by the expansion of the universe over billions of years. We simply couldn't build a mirror large enough on Earth to collect that dim, distant light. But we don't have to. The universe has already built these colossal lenses for us. By looking through these natural telescopes, we can effectively turn the James Webb into a telescope with a mirror the size of a galaxy cluster, allowing it to see details in infant galaxies that would otherwise be completely invisible. The most strategic targets for astronomers are these massive foreground galaxy clusters. Missions like the James Webb Space Telescope don't just point randomly into the dark. They carefully select areas of the sky known to contain these powerful gravitational lenses. One famous example is the galaxy cluster known as Webb's first deep field. In that single image, the distorted, stretched arcs of background galaxies are clearly visible, warped by the cluster's gravity. Many of those smudges of light are actually galaxies from when the universe was less than 5% of its current age, magnified and revealed solely because of this cosmic lensing effect. Looking ahead, this isn't just a fortunate happenstance we occasionally use. It's becoming a cornerstone of observational strategy. Future space missions are being planned with gravitational lensing as a primary tool. Astronomers are already creating detailed maps of the distribution of dark matter in these massive clusters to predict where the lensing effect will be strongest, identifying the sweet spots where magnification will be most extreme. This allows them to essentially book observation time on nature's own telescopes, planning to use these specific regions of space as windows to peer even further back, perhaps to see the very first stars igniting or to study the atmospheres of exoplanets in galaxies far beyond our own. We are moving from simply discovering these lenses to actively employing them in a coordinated campaign to map the invisible universe. This powerful tool isn't a one-size-fits-all phenomenon. It operates on a spectrum, and astronomers have learned to categorize and utilize its different flavors. The most dramatic and visually stunning type is known as strong gravitational lensing. This is what creates those multiple images of a single quasar and those perfect halo-like Einstein rings. Strong lensing requires a nearly perfect and powerful alignment, where the background object is almost directly behind a tremendously massive foreground lens like a galaxy cluster. The effect is unmistakable. It takes the light from the distant object and creates a cosmic funhouse mirror, producing multiple distorted and magnified copies. It's the universe's way of showing off, and for us, it's an invaluable magnifying glass. By studying these multiple images, scientists can not only see an incredibly distant galaxy, but also learn about its structure, its rate of star formation, and even its chemical composition, all thanks to the free magnification provided by the lens. But for every brilliant Einstein ring, there are countless subtler, more widespread distortions happening across the sky. This is the realm of weak gravitational lensing. Here, the alignments aren't perfect and the foreground masses are less concentrated. Instead of creating multiple distinct images, weak lensing just slightly stretches and shears the shapes of thousands upon thousands of background galaxies. To the untrained eye, these galaxies might just look a little odd or elongated, but to astronomers, this subtle, statistical distortion is the most powerful tool we have for mapping the invisible. The degree and direction of the stretching reveal the distribution of mass in the foreground, including the dark matter that we cannot see. By meticulously measuring the tiny, coherent distortions in the shapes of millions of galaxies, we can create vast three-dimensional maps of the dark matter web that forms the hidden skeleton of our cosmos, proving that what we see is truly only a fraction of what is there. Then there's the most fleeting and elusive type, microlensing. This occurs when a small, compact object like a star, a black hole, or even a planet drifts directly in front of a more distant star. Unlike its stronger cousins, the lens here isn't a gigantic galaxy cluster but a single, smaller object. Because it's so small, it doesn't create multiple images or dramatic arcs. That level of detail is far beyond our telescope's resolution. Instead, we see a very specific signature, a temporary brightening of the background star's light. As the lensing object moves across our line of sight, its gravity acts like a tiny magnifying glass, briefly focusing the star's light toward us and causing a characteristic spike in brightness that can last for hours, days, or weeks before fading away. This transient nature makes it a hunt, but an incredibly fruitful one. Microlensing is one of our best methods for detecting objects that emit no light whatsoever, from rogue planets wandering the galaxy alone to stellar mass black holes drifting silently in the dark. Each type of lensing requires different technology to detect. The dramatic arcs of strong lensing are unveiled by the incredible resolution of space telescopes like Hubble and James Webb, which can resolve the fine details of those distant distortions. Weak lensing, on the other hand, demands wide-field surveys. Projects like the ground-based Vera-C, Rubin Observatory are designed to photograph enormous swaths of the sky repeatedly, measuring the tiny shapes of billions of galaxies to compile the statistical data needed to trace the dark matter web. And microlensing campaigns rely on telescopes that can monitor millions of stars in crowded fields, like the center of our galaxy, watching for those telltale, unpredictable spikes in brightness that signal a hidden object's momentary passage. From the grandest cosmic scales to the hunt for invisible worlds, gravitational lensing in all its forms provides a unique window, allowing us to see the unseeable and chart the invisible. For centuries, the most compelling evidence for dark matter was indirect, like watching leaves swirl in the wind and knowing an unseen breeze must be causing it. We could see its gravitational effects, stars orbiting the centers of galaxies too quickly, entire galaxies moving within clusters at impossible speeds, but the substance itself remained a ghost. Gravitational lensing changed everything, transforming this ghost into a map we can now read. It provides the most direct and tangible proof that dark matter is not only real but forms the dominant architecture of our universe. The key lies in those subtle distortions of weak gravitational lensing. When astronomers train their powerful telescopes on a massive galaxy cluster, they see two things: the visible galaxies made of stars and gas, and the dramatic, stretched arcs of background galaxies bent by the cluster's total gravity, a gravity far stronger than the visible matter alone could possibly produce. By meticulously measuring the exact shapes and degrees of distortion in thousands of those background galaxies, scientists can perform a kind of cosmic reconstruction. They can calculate precisely how much mass must be present in the foreground cluster to warp the light by that specific amount, and they can pinpoint exactly where that mass is located. Time and again, the results are unequivocal. The vast majority of the mass creating these cosmic lenses is completely invisible. It does not emit, reflect, or absorb light. It is dark matter. This technique allows us to do something astonishing. We can now create detailed maps of this invisible material. By analyzing the lensing patterns, astronomers can illustrate where the dark matter is most densely concentrated and where it forms vast, diffuse halos extending far beyond the visible edges of galaxies. These maps reveal that dark matter isn't just a passive filler. It acts as the gravitational scaffolding for the entire cosmos. Every galaxy, every cluster of galaxies, is seated at the center of an immense, invisible nest of dark matter. This framework dictates the universe's large-scale structure, forming a colossal cosmic web of filaments and nodes where visible matter is merely the decorative icing tracing out the hidden cake beneath. This understanding completely reshapes our vision of the universe and our potential future within it. For future space travelers venturing beyond our galaxy, this invisible web isn't an abstract concept, it's a potential roadmap. The greatest concentrations of dark matter, the massive nodes and filaments of the cosmic web, create the deepest gravitational wells, the most powerful natural telescopes, and likely the most stable gravitational landmarks for long-distance navigation. Understanding this architecture is like a mariner learning the ocean currents. It could one day provide the most efficient and stable pathways for travel across the unimaginable voids between galaxies. The same phenomenon that allows us to see the universe's oldest secrets also charts the potential highways of our far future, all by illuminating the invisible hand that shapes everything. But the revelations from mapping dark matter were just the beginning. This same technique, this ability to measure the subtle warping of light across the cosmos, has handed us a tool to investigate an even more profound and mysterious force, dark energy. Think of dark matter as the invisible scaffolding pulling the universe together through gravity, while dark energy is the mysterious repulsive force that seems to be doing the exact opposite, pushing the universe apart at an ever-increasing rate. For decades, its existence was inferred from observing distant supernova, but gravitational lensing provides a completely independent and potentially even more powerful way to measure its influence and properties. The method relies on a cosmic census conducted across billions of years. Weak lensing doesn't just create a single, static map of dark matter. It allows us to create a whole series of them, a flipbook of the universe's structure at different epochs in its history. Remember, when we look at extremely distant galaxies, we are also looking back in time. Their light has traveled for billions of years to reach us. By measuring the weak lensing distortions from galaxies at different distances, and therefore from different eras, cosmologists can track how the large-scale structure of the universe has evolved. They can see how the cosmic web of dark matter has grown, how clusters have formed, and how filaments have stretched over the entirety of cosmic history. This growth is a titanic tug of war between the relentless pull of gravity, trying to clump matter together, and the aggressive push of dark energy trying to tear it apart. In the early universe, gravity was the dominant force. Matter coalesced, forming the first galaxies and the vast web we see mapped today. But as the universe expanded, dark energy's influence grew. Its repulsive effect acts as a sort of anti-gravity, working against the formation of new structure and stretching the very fabric of space itself. By precisely measuring the rate at which the cosmic web has grown, or more recently, stunted its growth, through these multi-epoch lensing maps, scientists can take the temperature of this cosmic battle. They can measure the strength of dark energy's push and how it has changed over time. The data from ambitious projects like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to provide this exact movie of the universe's evolution. By observing billions of galaxies and their distortions, these missions will create the most detailed three-dimensional map of the dark matter cosmos ever made, spanning nearly the entire age of the universe. The patterns etched into this map are like a fossil record of dark energy's influence. By analyzing how the clustering of matter has changed, scientists hope to determine the fundamental nature of dark energy itself, whether it is a constant force, as Einstein's cosmological constant suggests, or something far more dynamic and strange that evolves over time. The implications of this research stretch beyond pure cosmology and into the far future of humanity itself. Understanding dark energy is essentially about understanding the ultimate fate of everything. If dark energy continues to accelerate the universe's expansion, as current data suggests, we are likely heading toward a big freeze, where galaxies are pulled so far apart that the sky goes dark and the universe ends in cold, empty isolation. But if its properties are different, other fates are possible. And while it may sound like the stuff of distant speculation, unraveling the physics of this dominant energy could one day open doors to technologies we can scarcely imagine. The ability to understand or even manipulate the energy that comprises the majority of the cosmos could represent a leap in capability far greater than our mastery of electricity or nuclear power. It's a fundamental exploration of the engine driving reality itself, and gravitational lensing is providing one of our clearest windows into its workings. While the grand arcs of strong lensing map the universe's largest structures, the fleeting flashes of microlensing open a window to some of its smallest and most intriguing inhabitants, worlds beyond our solar system. This method excels at finding the otherwise unfindable, from planets circling distant stars to the truly enigmatic rogue planets, entire worlds drifting alone in the eternal night between stars. The process is a delicate and precise cosmic alignment. When a compact object like a star or even a planet passes directly in front of a more distant background star, its gravity acts as a temporary magnifying lens. For a period that might last just hours or days, it focuses the background star's light, causing a telltale, predictable brightening before the light returns to normal as the lens moves on. The beauty of this technique is its power to reveal planets regardless of their orbit or the light they emit. Unlike the transit method, which requires a planet to pass directly between its star and us, blocking a tiny fraction of the star's light, microlensing doesn't need that perfect alignment. And unlike the radial velocity method, which detects a star's wobble from a planet's gravitational tug, microlensing can find planets much further from their host stars. It can even detect planets orbiting at great distances in the frigid outer regions of their solar systems, places where other methods often fall short. But the most astonishing discoveries are the free-floating rogue planets. These are worlds that were likely flung from their nascent solar systems by gravitational interactions, and now they wander the galactic void alone. Microlensing is the only way we have to find these dark, orphaned worlds, and recent surveys suggest they are astonishingly common, perhaps even outnumbering stars in our galaxy. Some of the most exciting microlensing discoveries have been of planets that bear a striking resemblance to our own. By carefully analyzing the subtle light curve of a microlensing event, astronomers can decipher the signature of not just the foreground star, but also any planets orbiting it. This has led to the identification of several rocky, Earth-mass planets orbiting within the habitable zone of their star, that Goldilocks region where temperatures could allow for liquid water to exist on the surface. These are not the close-in, scorched worlds often found by the transit method. These are potential analog Earths orbiting at Earth-like distances from stars similar to our Sun. For future generations looking to the stars, these discoveries are more than just data points. They are potential destinations. They represent candidate worlds for long-term study, places where we might one day send robotic probes or even, in the far future, establish outposts. They are also our best targets in the search for biosignatures, atmospheric chemicals like oxygen or methane that could hint at the presence of life. The hunt for these distant worlds is a global endeavor, relying on a network of telescopes constantly monitoring dense star fields like the bustling center of our Milky Way. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and the Korea Microlensing Telescope Network, or KMT-NET, tirelessly watch millions of stars, their robotic eyes scanning for those critical, unpredictable flashes that signal a lensing event. When one is detected, astronomers around the world are alerted to turn their telescopes toward it, collaboratively tracking the light curve to extract every possible detail about the lensing object. This international cooperation has transformed microlensing from a curious theoretical possibility into a robust and highly productive branch of astronomy, one that is painting a much more diverse and surprising picture of planetary systems across the galaxy. It reveals a cosmos teeming with worlds, many in environments utterly different from our own, expanding our understanding of where and how planets can form and what kind of strange, lonely wonders might be waiting in the dark. Perhaps the most profound gift of gravitational lensing is its ability to function as a time machine, offering us a direct view into the childhood and adolescence of galaxies. We know that looking deep into space is also looking back in time, but for the most distant and therefore earliest galaxies, their light is incredibly faint, stretched into near invisibility by the expansion of the universe. It would be like trying to read the history of our world by studying a single, dying ember from its first fire. Gravitational lensing changes that completely. By magnifying these faint, ancient objects, it's as if that ember has been fanned into a bright flame, giving us a clear, detailed view of the universe's formative years. This magnification allows us to witness the very processes that build galaxies over billions of years. In high-resolution images from the Hubble and now the James Webb Space Telescope, we don't just see smudges of light, we see the intricate details of these adolescent galaxies. We can resolve their structures, spotting delicate spiral arms beginning to wind, massive clumps of star-forming gas and dust, and the brilliant glow of stellar nurseries where new suns are being born at a ferocious rate. This is a stark contrast to the more sedate pace of star formation in mature galaxies like our own Milky Way. These early galaxies are chaotic, dynamic, and incredibly active, and without the magnifying power of a foreground lens, these crucial details would be lost to us. A key discovery has been the role of mergers in galactic evolution. The early universe was a far more crowded and violent place, and galaxies frequently collided and merged in spectacular cosmic crashes. Gravitational lensing allows us to see these events unfold in real time, albeit over millions of years. We can observe the tidal tails of stars being ripped from galaxies during close encounters, the violent compression of gas clouds triggering immense waves of new star formation, and the eventual coalescence of two distinct systems into a single, larger galaxy. This process is fundamental to how galaxies grow. Our own Milky Way is a product of such mergers, having consumed smaller dwarf galaxies throughout its history, and it is on a collision course with the neighboring Andromeda galaxy billions of years from now. Through lensing, we are watching the very same process that shaped our home happen in the distant past. Beyond just their structure, lensing lets us perform a kind of cosmic autopsy on these galaxies, analyzing their chemical composition. By studying the spectrum of their magnified light, astronomers can determine what elements are present. The earliest galaxies are metal-poor, meaning they are dominated by the primordial hydrogen and helium forged in the Big Bang. As generations of stars live and die within them, exploding as supernova and seeding their surroundings with heavier elements like carbon, oxygen, and iron, the galaxies become more enriched. By tracking this metallicity across cosmic time, from the earliest lensed galaxies to more recent ones, we can create a timeline of how galaxies have chemically evolved, directly tracing how they have grown more complex and capable of forming rocky planets and potentially life. This unprecedented view is fundamentally rewriting our models of galaxy formation. For a long time, theories suggested that galaxies grew slowly and steadily, accumulating gas and forming stars at a predictable pace. But the detailed observations made possible by gravitational lensing reveal a much more dynamic and rapid story. It appears that some of the earliest galaxies grew to immense sizes astonishingly quickly, a phenomenon that challenges our previous understanding of the dark matter halos that facilitate their growth. Each new lensed galaxy we study is another data point, another piece of the puzzle, helping us refine our simulations and understand the complex interplay of dark matter, gas, star formation, and black holes that governs the life cycle of every galaxy in the universe. Peering back to the very dawn of cosmic structure, gravitational lensing grants us a front-row seat to the universe's infancy, a period once thought to be forever beyond our observational reach. The most distant galaxies, whose light has been traveling for over 13 billion years to reach us, are not only incredibly faint, but their light is stretched into the infrared part of the spectrum by the relentless expansion of the universe. This combination makes them nearly impossible to detect with conventional telescopes, but by using massive galaxy clusters as natural magnifying glasses, we can overcome these limitations. The lens amplifies their faint light, bringing into focus details we could otherwise only theorize about, effectively turning our most powerful observatories into hypersensitive time machines. Studying these magnified infant galaxies has revealed a universe far more dynamic and chaotic in its youth than we ever anticipated. We see galaxies that are not the elegant, well-ordered spirals and ellipticals we observe in the modern universe, but rather small, clumpy, and irregular structures. They are undergoing ferocious bouts of star formation, creating new suns at a rate hundreds of times faster than our own Milky Way does today. These are not the serene islands of stars we know. They are cosmic fireworks displays, blazing with the intense energy of countless new stars igniting within swirling clouds of primordial gas and dust. This frantic activity suggests the early universe was a place of rapid construction, where galaxies assembled themselves with a speed and violence that challenges some of our previous models. Beyond their structure and activity, the magnified light from these ancient objects allows us to perform a kind of cosmic chemistry. Using a technique called spectroscopy, we can split the lensed light into a rainbow spectrum and read the unique chemical fingerprints within it. The earliest galaxies show a striking simplicity in their composition. They are dominated by the basic elements forged in the Big Bang itself, hydrogen and helium. They are virtually devoid of the heavier elements like carbon, oxygen, and iron that are essential for forming rocky planets and ultimately life as we know it. This tells a profound story about cosmic evolution. These first galaxies are the universe's pioneers, the first factories that would eventually forge these heavier elements in their stellar cores and through their supernova deaths, seeding the cosmos with the raw materials for everything that would follow, including us. This direct view into the past is fundamentally reshaping our understanding of our own cosmic origins. Every element in our bodies, every planet in our solar system, was created in the heart of a star that lived and died long before our sun was born. By studying these first generations of stars within their lensed host galaxies, we are tracing our own lineage back to its source. We are beginning to understand the conditions that allowed our galaxy, our star, and our planet to eventually form. Gravitational lensing does more than just show us the ancient universe. It connects us to it directly, revealing the long and intricate chain of events that led from a hot, dense state of pure energy to a universe rich with complexity and life. It provides the empirical evidence for our own place in the grand story of cosmic evolution. But perhaps the most profound use of this natural phenomenon is as a universal proving ground, a way to test the very laws of physics under conditions so extreme they are impossible to recreate in any laboratory on Earth. Gravitational lensing provides a unique observational check on our most fundamental theories, including Einstein's general relativity, by allowing us to see how gravity behaves in the most intense environments imaginable around supermassive black holes and in the vast, dense regions of the early universe. For decades, general relativity has passed every test with flying colors, from the orbit of Mercury to the timing of GPS satellites. But a major question remains: is it the complete and final theory of gravity, or is it an approximation that might break down under the most extreme conditions? The regions around black holes, where gravity is so powerful that not even light can escape, are the ultimate testing grounds. Here, space-time isn't just curved, it is twisted and warped into a singularity. By carefully studying how light from distant stars and galaxies is lensed as it passes near these monstrous objects, astronomers can map the space-time curvature with incredible precision. They can check if the observed bending of light matches the predictions of general relativity exactly, or if there are tiny deviations that might point toward new physics, perhaps the first hints of a connection between gravity and quantum mechanics, a unified theory that has eluded scientists for a century. These tests are already underway. The Event Horizon Telescope collaboration, famous for capturing the first image of a black hole's shadow, also uses the principles of lensing to understand the environment around it. The bright ring seen in that historic image is itself a lensing effect caused by light being bent around the black hole. By analyzing the precise size and shape of that ring, scientists can verify if it conforms to the predictions of general relativity for a black hole of that mass. So far, Einstein's theory holds strong, but with more precise observations and more black holes to study, we might one day find a crack in the foundation, a place where the universe itself shows us that our understanding is still incomplete. Beyond black holes, lensing offers a way to probe the validity of general relativity on the largest of scales. Some alternative theories of gravity predict that the strength of gravity might vary over cosmic distances, or that the way dark matter interacts with gravity could be slightly different. These differences would be too subtle to measure in our solar system, but would leave an imprint on how the large-scale structure of the universe forms and evolves. The weak lensing maps that trace the cosmic web of dark matter are incredibly sensitive to these effects. By comparing the observed growth of structure revealed through multi-epoch lensing surveys with the predictions of different gravitational theories, cosmologists can perform a grand cosmological test. It's a way of asking the universe directly which set of rules it is following. This research touches on one of the biggest mysteries in modern physics, the nature of dark energy. Is the accelerating expansion of the universe driven by a constant energy inherent to space itself, as Einstein proposed, or is it caused by a weakening of gravity's grip on enormous scales? Precise measurements from future lensing surveys like those from the Euclid mission are designed to distinguish between these possibilities. The data will provide a definitive measurement of how the rate of structure formation has changed over billions of years, which in turn will tell us if gravity behaves exactly as we think it does across the vast cosmic voids. Each distorted galaxy image is a data point in the universe's own experiment, and we are the observers, meticulously recording the results to decipher the fundamental laws that govern everything from the smallest particles to the entire cosmos. Now we're standing at the brink of a new observational frontier, where two of Einstein's most profound predictions are converging to create a tool of unimaginable power. For decades, we've studied the universe by observing light, from radio waves to gamma rays. But light is only one messenger. In 2015, we opened a completely new window on the cosmos by directly detecting gravitational waves, the ripples in spacetime itself, caused by cataclysmic events like the collision of black holes. This was like giving the universe a voice, allowing us to hear its most violent events. Now, imagine combining that sense of hearing with the magnifying vision of gravitational lensing. We are beginning to listen for the echoes of these cosmic crashes as they are bent and amplified on their way to us, creating a new field that promises to resolve some of the biggest arguments in modern cosmology. The principle is the same as with light, but the messenger is different. When a pair of massive objects like neutron stars or black holes spiral into each other, they don't just give off a flash of light. They shake the very fabric of spacetime, sending out waves that travel at the speed of light across the universe. If those waves pass through the warped spacetime around a massive galaxy cluster or a supermassive black hole on their journey to Earth, their path will be bent. This gravitational lensing of the waves would create a remarkable effect. We wouldn't detect just one signal, we could detect the same cataclysm multiple times. The lens would effectively create copies of the event, with each copy arriving at a slightly different time because the waves would have traveled along paths of different lengths around the massive lens. Detecting these lensed echoes would be a game-changer for measuring cosmic distances with unparalleled precision. A gravitational wave signal carries within it a direct record of the masses of the objects that created it and the amplitude of the waves, which tells us how much energy was released. By comparing the intrinsic strength of the signal with how weak it appears when it reaches us, astronomers can calculate the distance to the source, a method often called a standard siren, analogous to how a standard candle works with light. But if that same siren is lensed, we get multiple identical distance measurements from the same event, just arriving on different days. This provides an incredibly robust calibration point. By combining this precise distance with the redshift of the lensing galaxy, which tells us how much the universe has expanded since the light from that galaxy left it, we get a direct measurement of the Hubble constant, the rate of the universe's expansion. This could finally settle the ongoing Hubble tension, where different methods of measuring the expansion rate persistently disagree, potentially pointing toward new physics beyond our current understanding of the cosmos. Furthermore, the nature of the lensing itself would reveal secrets about the lens. The time delay between the multiple copies of the gravitational wave signal is exquisitely sensitive to the mass distribution of the lensing object. By analyzing these delays, we could weigh the invisible dark matter halo of the foreground galaxy cluster with incredible accuracy, even mapping its substructure. This would be a powerful, independent way to study dark matter, using the whispers of space-time itself as our probe, but the potential discoveries go even deeper. The waves are also affected by the properties of the particles they pass through in a way that light is not. Studying how a lensed gravitational wave signal might be slightly altered could provide clues about the nature of dark matter particles themselves, testing whether they interact with each other in ways we haven't yet predicted. We are already building the observatories capable of hearing these echoes. The current generation of detectors like LIGO, Virgo, and CAGRA are constantly being upgraded to greater sensitivities. The next generation, such as the Einstein telescope and the space-based LISA observatory, will be so sensitive that they could detect tens of thousands of events every year. With that volume of data, the statistical probability of catching several strongly lensed events becomes very high. We are on the cusp of moving from simply hearing the universe's loudest crashes to using their magnified echoes as precision tools for cosmology, transforming our understanding of distance, expansion, and the invisible matter that guides it all. This next chapter in our exploration of the cosmos is already being written, with a new generation of observatories specifically designed to harness the power of gravitational lensing on an unprecedented scale. Leading this charge is NASA's and Nancy Grace Roman Space Telescope, often called the sister to Hubble and Webb, but with a very different and equally powerful specialty. While Webb peers deeply at small areas of the sky, Roman is designed for breadth. Its wide-field instrument will perform massive surveys, capturing the equivalent of 100 Hubble deep fields in a single shot. This enormous scope is crucial because mapping dark matter through weak lensing is a numbers game. You need to meticulously measure the subtle distortions in the shapes of billions of galaxies to trace the invisible web. Roman will do exactly that, creating a map of the dark matter distribution across a vast portion of the universe with stunning precision, effectively giving us our first high-resolution census of the cosmos's hidden skeleton. Simultaneously, the European Space Agency's Euclid mission is undertaking a complementary and equally ambitious endeavor. Launched in 2023, Euclid is a dark universe detective, engineered to explore the twin mysteries of dark matter and dark energy. Its mission is to measure the shapes and redshifts of over 1 billion galaxies, tracing the expansion history of the universe over the last 10 billion years. By observing how the weak lensing signal has evolved over this immense cosmic timeline, Euclid's data will allow scientists to measure the strength and nature of dark energy with unprecedented accuracy. Is it a constant force or does it vary over time? The subtle patterns etched into the distortions of those billion galaxies hold the answer, and Euclid is our key to deciphering them. On the ground, the Vera C. Rubin Observatory is set to join this grand collaboration, bringing a truly monumental capability to the table. Its 8.4-meter mirror and massive 3.2 gigapixel camera are designed to photograph the entire available southern sky every few nights for a decade. This legacy survey of space and time, or LSST, will be the largest astronomical movie ever made, a dynamic map of the cosmos in motion. For lensing, this is revolutionary. It will detect tens of thousands of new strong lensing events, Einstein rings and arcs, that were too faint or rare for previous surveys to find. But more importantly, by repeatedly imaging the same sky, it will catch the fleeting brightening of microlensing events in unprecedented numbers, potentially discovering thousands of rogue planets and other dark, compact objects lurking in the galactic halo. The true power of these missions, however, lies not in their individual efforts but in their synergy. Imagine Roman and Euclid in space along with Webb, creating exquisitely detailed, multi-wavelength maps of the dark matter web. Then, the Rubin Observatory on the ground provides the incredibly deep time domain context, monitoring how these lensed objects change over time. By combining their datasets, astronomers will be able to perform a kind of cosmic tomography, building a three-dimensional, time-evolving model of the dark universe. This multi-messenger approach to lensing will cross-check results, eliminate systematic errors, and provide a level of certainty about our models that we've never had before. The data from these observatories won't just add to our knowledge, it will fundamentally revolutionize it. They will provide the evidence needed to potentially settle the Hubble tension, the nagging discrepancy in the universe's expansion rate, which could point toward new physics beyond our current standard model of cosmology. They could reveal if dark matter particles interact with each other in subtle ways, or finally determine the true nature of dark energy. This isn't just about mapping what's out there, it's about rigorously testing the fundamental rules of reality itself. We are on the verge of a golden age of discovery where these magnificent machines, designed to read the subtle distortions of light, will illuminate the darkest secrets of our universe. Yet with every new window we open onto the cosmos, we are met with an overwhelming flood of data. The Vera C. Rubin Observatory alone is expected to generate over 20 terabytes of data every single night, compiling a catalog of tens of billions of galaxies. Within that ocean of information are hidden the subtle, telltale distortions of gravitational lensing, the faint arcs, the multiple images, the statistically sheared shapes of distant galaxies. Finding these cosmic signatures by eye would be like searching for a specific grain of sand on all the beaches of Earth. It's an impossible task for any human team, which is why the next great revolution in this field isn't happening in a telescope dome, but in the world of artificial intelligence and machine learning. These advanced algorithms are the only tools powerful enough to sift through the monumental datasets from modern surveys. They are trained to recognize the unique visual fingerprints of lensing that would often be too subtle for even the most experienced astronomer to spot. The process starts by feeding these AI systems thousands of confirmed examples of strong lensing, beautiful Einstein rings and dramatic arcs, as well as millions of images of normal, undistorted galaxies. The algorithm learns through a process of pattern recognition far more nuanced than any simple filter. What a gravitational lens looks like, it isn't just searching for a perfect ring. It's learning to identify the specific kinds of warping, the symmetrical distortions, and the unusual alignments of light that signal the presence of a hidden cosmic lens. Once trained, these AIs can scan new astronomical images at incredible speeds, flagging potential candidates with an efficiency that dwarfs human capability. But their role goes far beyond just discovery. The real magic happens in the analysis, determining the precise properties of a lensing system, calculating the mass of the foreground dark matter halo, modeling how it's distributed, and reconstructing the true shape of the magnified background galaxy requires solving incredibly complex inverse problems. It's like being given a handful of distorted, funhouse mirror reflections and trying to mathematically reconstruct both the original object and the exact shape of the mirror that warped it. Machine learning models are uniquely suited to this task, running through millions of possible configurations to find the model that best fits the observed data, giving us a precise and detailed map of the invisible matter doing the lensing. This synergy between human curiosity and artificial intelligence is accelerating our progress at an exponential rate. What once took years of painstaking manual analysis by large teams can now be done in a fraction of the time with ever-increasing accuracy. These algorithms are also becoming predictive. By analyzing the patterns in existing lensing maps, AIs can now forecast where we are most likely to find new and even more powerful natural telescopes in the sky, guiding where we point our most valuable instruments like the James Webb Space Telescope. We are moving from an era of discovery into an era of automated, intelligent exploration, where AI acts as our tireless digital assistant, combing through the heavens to find the most interesting cosmic mysteries for us to then study in profound detail. This partnership is essential, turning the raw, overwhelming fire hose of data from our new observatories into a refined stream of groundbreaking discovery. What's truly remarkable is that this grand endeavor to map the invisible universe isn't just for professional astronomers with PhDs and access to giant telescopes. You sitting at home can actually be a part of this cosmic discovery. Projects like space warps have brilliantly tapped into the unique power of the human brain to recognize patterns that even the most advanced algorithms can sometimes miss. These citizen science initiatives invite anyone with an internet connection and a sense of curiosity to sift through real data from massive sky surveys, like those from the Hubble Space Telescope or the soon-to-be operational Vera-C. Rubin Observatory, the task is deceptively simple. You're presented with an image of a patch of sky and asked to look for the faint, telltale arcs and smudges that signal a gravitational lens. It's a cosmic version of Where's Waldo, but instead of finding a man in a striped shirt, you're helping to find the hidden scaffolding of the cosmos. The discoveries made by this global army of amateur scientists are nothing short of astounding. In one famous case, a Dutch schoolteacher named Hanny van Arkel was participating in the Galaxy Zoo project when she noticed a strange, glowing green object near a distant galaxy. This object, now famously known as Hanny's voorwerp, which is Dutch for Hanny's object, turned out to be a cosmic ghost, a vast cloud of gas illuminated by the light from a quasar that had since gone dormant. It was a completely new astronomical phenomenon discovered by a curious volunteer. In the context of gravitational lensing, citizen scientists have identified hundreds of potential lens candidates that automated algorithms had overlooked. The human eye is exceptionally good at spotting the subtle, often imperfect curves and symmetrical distortions that characterize a lensed system, especially in messy, complex regions of space where galaxies overlap. These volunteer discoveries are then passed on to professional astronomers for follow-up confirmation with powerful telescopes, turning a curious click into a genuine contribution to astrophysics. This model of crowd-sourced science is set to become even more critical in the near future. As we've discussed, new observatories like the Vera-C, Rubin Observatory will generate a truly staggering amount of data, millions of images containing billions of galaxies. While AI will do the heavy lifting of the initial scan, there will always be unusual, one-of-a-kind lensing events that fall outside the training data of machine learning models. These are the cosmic oddballs, the rare and unexpected configurations that could lead to the most groundbreaking discoveries. By engaging the public, astronomers are effectively deploying a massive, distributed supercomputer made of human brains, one that excels at creativity, intuition, and recognizing the unusual. This partnership between human and artificial intelligence creates a powerful, two-tiered discovery system that ensures we miss as little as possible. Beyond the raw scientific output, these projects perform a vital function. They democratize discovery. They create a direct, personal connection between individuals and the vast, often impersonal, enterprise of modern science. There's a profound sense of wonder in knowing that you might be the first person in all of human history to lay eyes on a particular gravitational lens, a specific warp in space-time that reveals a hidden galaxy. It transforms the public from passive consumers of science news into active participants in the process of exploration. For the next generation of potential scientists, it can be the spark that ignites a lifelong passion for the cosmos. As our datasets grow ever larger, this collaborative spirit between professional researchers and citizen scientists will be essential, ensuring that every pair of eyes, whether trained or simply curious, can help us piece together the magnificent puzzle of our invisible universe. This process of cosmic cartography is where the true power of gravitational lensing comes into its own, transforming from a fascinating optical effect into our most advanced tool for building a three-dimensional atlas of everything. It's one thing to know that dark matter exists. It's another to be able to plot its precise location, density, and structure across billions of light years. To create these maps, scientists don't rely on lensing alone. They perform a kind of astronomical triangulation, combining the distortion data from weak gravitational lensing with another crucial piece of information: redshift. Redshift is a measure of how much the light from a galaxy has been stretched by the expansion of the universe, and it acts as a direct indicator of its distance from us. By measuring the redshift of both the background galaxies being lensed and the foreground galaxies doing the lensing, astronomers can assign a precise location in three-dimensional space to every data point. Imagine having a vast dark cloud whose shape you can't see. Now, imagine you have millions of tiny lights placed at known distances behind that cloud. By observing how the light from each of those tiny bulbs is distorted as it passes through the cloud, you can mathematically reconstruct the cloud's exact shape and density in 3 dimensions. That is precisely what cosmologists are doing on a universal scale, using billions of galaxies as their background lights and the warping of their shapes to trace the invisible dark matter cloud enveloping them. The resulting maps are nothing short of breathtaking. They reveal the cosmic web in stunning detail, a vast, intricate network of dark matter filaments connecting massive galaxy clusters at their nodes, with enormous voids of relatively empty space stretching between them. This web is the fundamental architecture of the cosmos, the framework upon which all visible structure is built. For the first time in human history, we are moving from theoretical models to an observational chart of this hidden universe, seeing the true skeleton of creation. These maps are far more than just a beautiful picture. They are functional tools that are already reshaping our understanding of physics. By comparing the observed growth of this web over cosmic time, as seen through lensing surveys at different redshifts, to the predictions of supercomputer simulations, scientists can perform stringent tests on our entire cosmological model. They can measure the lumpiness of the universe, the rate at which clusters merge, and the pull of gravity on the largest scales, looking for any discrepancies that might hint at new physics or a need to modify our understanding of dark energy or even Einstein's theory of gravity itself. Looking toward a future of interstellar travel, these 3D maps could one day become the fundamental charts for galactic navigation. The most stable and predictable gravitational features in the galaxy are not the stars which are born, live, and die, but the massive, slow-moving halos of dark matter. These halos create the deepest and most consistent gravitational wells in space. For a spacecraft traveling between stars and eventually between galaxies, following the gravitational contours laid down by this dark matter web could provide the most efficient and stable pathways, much like a sailor using ocean currents rather than fighting against them. The same maps that reveal the universe's deepest secrets today might one day guide our first journeys into the interstellar void, turning our theoretical understanding of the cosmos into a practical guide for exploration. But even the stunning magnification of entire galaxies is just the beginning. The most spectacular and scientifically valuable lensing events occur on a far more intimate scale, when the cosmic alignment is so perfect that it doesn't just magnify a galaxy, it zooms in on a single, individual star within it. These are the extreme magnification events, where the natural telescope focuses with such incredible precision that a star billions of light years away can, for a brief moment, become one of the brightest points in the sky, magnified not by dozens but by thousands of times. Achieving this requires a flawless and rare convergence, a massive foreground object like a galaxy cluster to create the main lens, and then within that cluster, a single star or a compact object like a black hole must drift directly into the line of sight, acting as a secondary lens within the primary one. This double lensing effect is like using a magnifying glass on top of a telescope, and the resulting flash of light can be utterly extraordinary. One of the most famous examples of this is the star nicknamed Icarus, officially known as Max J1, 149 lensed star 1. Its light traveled for 9 billion years before it reached us. Under normal circumstances, it would have been completely invisible, lost in the glow of its host galaxy. But the gravity of a massive foreground galaxy cluster magnified its light about 600 times. Then, something even more incredible happened. Another compact object within the cluster, likely a star or a stellar remnant, passed almost perfectly through the line of sight. This added a second layer of magnification, boosting Icarus's brightness by a further factor of thousands. For a short time, this single, ancient blue supergiant star became visible to the Hubble Space Telescope, a pinprick of light from the universe's youth suddenly blazing into view. It was like spotting the flame of a single candle from the distance of the moon. The scientific value of catching these fleeting cosmic miracles cannot be overstated. For the few weeks or months that such an event lasts, astronomers can perform a detailed forensic analysis on a star from a time when the universe was very young. By dissecting its light through spectroscopy, they can determine its temperature, its mass, its composition, and even its stage of life. Studying individual stars like Icarus allows us to test our models of stellar evolution in an environment completely different from our own galactic neighborhood. We can answer fundamental questions. Were the first generations of stars different? Did they form with different compositions, burn hotter, or live shorter, more violent lives? Each extreme lensing event is a pristine time capsule, offering a direct look at the building blocks of early galaxies, one star at a time. Monitoring the sky for these events has become a dedicated scientific pursuit. Projects like the Hubble Space Telescope's RELIX program and observations with the James Webb Space Telescope are deliberately targeting massive galaxy clusters, knowing they are the most likely stages for these spectacular magnifications to play out. The strategy involves taking repeated images of these clusters over time, watching for any new points of light that suddenly appear, brighten dramatically, and then fade away. It's a patient hunt for the most powerful and temporary cosmic flares, each one a potential Rosetta Stone for understanding stellar physics across cosmic time. The data gathered doesn't just tell us about the background star. The very nature of the brightening curve reveals intricate details about the foreground lensing object as well, often providing our only way to detect and weigh invisible isolated black holes or dense neutron stars wandering through the halos of galaxy clusters. In this way, a single flash of light illuminates both the incredibly distant and the mysteriously dark, connecting the evolution of stars to the hidden architecture of the universe itself. Yet these cosmic lenses do more than just reveal the grand architecture of the universe. They offer a chance to probe its most fundamental nature, down to the very fabric of space-time. For all its success, Einstein's theory of general relativity, which describes gravity as the curvature of space-time, has one major gaping hole. It doesn't play nicely with quantum mechanics, the set of rules governing the subatomic world. At the enormous scales of planets, stars, and galaxies, gravity behaves exactly as Einstein predicted. But physicists are certain that at the tiniest scales, near the core of a black hole or at the very moment of the Big Bang, gravity itself must become grainy or quantum. The problem is, we have no idea how to observe this. Gravitational lensing might be the key that finally unlocks this door. The most promising place to look for these quantum effects is where gravity is at its most extreme, around black holes. The region immediately surrounding a black hole's event horizon is where space-time is warped more violently than anywhere else in the universe. According to some cutting-edge theories, this intense environment is where the smooth, continuous space-time of general relativity might begin to show its quantum underpinnings. It might become subtly pixelated or foamy, like the surface of a bubbling liquid when viewed incredibly closely. This quantum foam, if it exists, would be immeasurably small, but its effects could potentially be detected by studying how light behaves as it is lensed around a black hole. Imagine a single photon, a particle of light, on a billion-year journey that takes it grazing past the event horizon of a supermassive black hole. According to classical general relativity, its path will be bent by a very specific calculable amount. But if spacetime itself has a quantum graininess at that scale, the photon's path might be minutely altered. It might scatter in a way that wouldn't be predicted by Einstein's equations alone. By observing the light from distant quasars that has been lensed by intervening black holes, and by measuring its properties with exquisitely precise future instruments, astronomers might one day detect a statistical anomaly, a slight fuzziness or an unexpected pattern in the lensed images that points toward this quantum nature of gravity. This isn't just abstract theoretical work. Missions like the Next Generation Event Horizon Telescope Network and future space-based gravitational wave observatories are being designed with the sensitivity to test these very ideas. They will measure the lensing of light and the ringing of spacetime around black holes with a precision we can barely conceive of today, searching for any deviation from Einstein's predictions. Finding even the smallest discrepancy would be a monumental breakthrough, providing the first experimental evidence for a theory of quantum gravity. It would confirm that spacetime is not a smooth, continuous stage, but is instead woven from something more fundamental. The implications of such a discovery would ripple far beyond astrophysics, potentially seeding technologies that sound like pure science fiction. Harnessing the principles of quantum gravity could lead to a revolution in energy generation, propulsion, and even communication. If we can understand how gravity operates at the quantum level, we might learn to influence it. The ability to manipulate gravitational fields, even slightly, could pave the way for inertia dampeners, artificial gravity on spacecraft, or propulsion systems that don't rely on expelling mass. While these applications remain firmly in the realm of distant speculation, they all share a common requirement: a definitive theory of quantum gravity built upon empirical evidence. The subtle distortions captured by gravitational lensing around black holes might provide the first crucial data points for that theory, turning the most profound cosmic lenses into our most powerful microscopes, revealing the hidden quantum heart of reality itself. This same principle of cosmic focusing that lets us see across the universe might one day be our best tool for talking across it. For any civilization looking to send a message across the mind-boggling voids between stars, the fundamental problem is the same: signal degradation. A transmission beamed from even our closest stellar neighbor, Proxima Centauri, would spread out and weaken so dramatically by the time it reached us that it would be almost indistinguishable from background cosmic static. It would be like trying to have a conversation with someone on the other side of a roaring stadium by whispering, but what if you could borrow a cosmic megaphone? Or more accurately, a cosmic satellite dish. That's precisely what gravitational lensing offers. The most promising focal point in our own solar system isn't something we built, it's our sun. According to Einstein's theories, the sun's gravity creates a lensing effect. bending and focusing any electromagnetic waves that pass around it. This creates a gravitational focus, a region in space where signals from behind the sun would be dramatically amplified. The focal line starts at a staggering distance of about 550 astronomical units from the sun. That's over 14 times further out than Pluto. It's a daunting distance for a spacecraft, but it's not an impossible one. A probe placed at that specific point could use the sun's gravity as a natural telescope to peer into the universe with unparalleled clarity, or conversely, as a colossal antenna to broadcast a message with incredible power and precision. Instead of broadcasting a signal in all directions and hoping someone hears a faint whisper, a transmitter at the solar gravitational focus could aim a tightly focused, immensely powerful beam at a specific target star system, making interstellar communication far more feasible. Now expand that idea to a Type 2 or Type 3 civilization on the Kardashev scale, one that has mastered energy on a stellar or galactic level. Such an advanced society wouldn't be limited to using their own star. They could identify a network of ideal gravitational lenses throughout the galaxy-specific neutron stars or black holes with precisely known masses, and position relays near their focal points. This would create a kind of interstellar internet, a gravitational lensing network where signals are caught, massively amplified, and retransmitted from one natural amplifier to the next, allowing for clear communication across thousands of light years without the signal ever degrading to noise. A civilization could effectively turn the galaxy's most massive objects into a series of signal boosters, making the entire Milky Way a much smaller, more connected neighborhood. For us, the search for extraterrestrial intelligence, or SETI, might be looking in the wrong places. Instead of just scanning random frequencies from the general direction of a star, a more targeted approach would be to listen at the specific focal points of other stars. If an advanced civilization is using its star as a transmitter, the signal would be strongest along a very narrow, very specific line in space extending from that star. Our best chance of hearing a message might be to precisely calculate where that focal line passes through our solar system and point our receivers there, listening for a signal that is being deliberately aimed at us using their own sun's gravitational lens. This transforms the search from a wide-band scan of the entire sky to a highly specific hunt for a needle in a cosmic haystack, but it gives us a much better idea of exactly what that needle looks like and where it should be. The implications for our own future are equally profound. If we ever hope to make contact or send a coherent message of our own, the gravitational lens of our sun provides the most powerful amplifier we could ever hope to build. A project to send a probe to the sun's gravitational focus is already being seriously studied by organizations like NASA, a Jet Propulsion Laboratory, and initiatives such as the Breakthrough Starshot program. While the primary mission would be unparalleled astronomical observation, the communications potential is a cornerstone of the concept. Such a probe could act as our first interstellar messaging station, allowing us to finally participate in a galactic conversation, not just listen for one. It represents a future where humanity moves from being a silent observer of the cosmos to an active participant, using the subtle warp of space-time itself to finally say hello. These multiple images don't just arrive at our telescopes all at once. They each take a slightly different path around the massive gravitational well of the lens. And because those paths are of different lengths, the light from each image takes a different amount of time to complete its journey to us. This creates a time delay, a stagger of days, weeks, or even years between when we see the first image of an event appear and when we see its identical copy pop up elsewhere in the lensed system. It's the ultimate cosmic replay, and by carefully measuring this delay, we gain access to a treasure trove of information. The process is akin to having multiple witnesses to a single event, each located at a different distance from it. By noting the precise differences in the time their accounts arrive, you can triangulate the location of the event itself. In cosmology, the event is the distant supernova or quasar, and the time delay between its multiple images is exquisitely sensitive to the total mass of the lensing object, including all of its invisible dark matter. By modeling the mass distribution of the foreground galaxy cluster and then comparing the predicted time delays to the ones we actually observe, we can weigh the cluster with incredible accuracy. This gives us a direct, dynamic measurement of mass that is completely independent of other techniques, providing a crucial check on our models of both visible and dark matter. But the real power of this method extends far beyond just weighing lenses. Once we have a precise model of the lens's mass, we can use it to perform one of the most precise measurements in all of cosmology, calculating the Hubble constant. This is the number that describes the current expansion rate of the universe, and it's been the source of a major puzzle. Two primary methods for measuring it, one using the cosmic microwave background and another using supernova in the local universe, have persistently given slightly different answers. This discrepancy, known as the Hubble tension, could be a mere observational fluke, or it could be our first hint of new physics beyond our standard model of cosmology, perhaps a new type of particle or a previously unknown property of dark energy. Time delay cosmography offers a completely independent and direct way to measure the Hubble constant, acting as a potential tiebreaker. Here's how it works. The measured time delay between images depends on two things: the geometry of the lens and the overall scale of the universe, which is governed by the Hubble constant. Once we've used the first image to precisely map the lens's mass and geometry, the time delay to the subsequent images becomes a direct ruler for cosmic distance. A longer delay implies the light has traveled a greater relative distance, which points to a specific expansion rate. By monitoring these cosmic replays in lensed quasars, astronomers can effectively read the Hubble constant directly from the sky. This technique is already yielding remarkably precise results. Systems like the lensed quasar SDSS-J12266+2009 have been monitored for years, with astronomers patiently waiting for one image to brighten after another. The data from these systems is helping to narrow the gap between the other measurement methods, and as we add more of these cosmic clocks to our sample, the precision will only improve. Future observatories will discover hundreds, perhaps thousands, of these time delay lenses, providing a robust network of independent measurements that will either resolve the Hubble tension or, if the discrepancy holds, provide overwhelming evidence that we are indeed missing a fundamental piece in our understanding of the universe's expansion. It turns a curious feature of warped space-time into one of our most powerful tools for deciphering the ultimate fate of everything. But the story doesn't end with light and gravity. The true power of modern astronomy lies in its ability to listen to the universe across multiple channels, and gravitational lensing is now acting as the ultimate amplifier for these other cosmic messengers as well. For decades, we've studied the cosmos almost exclusively through light, from radio waves to gamma rays. But now, we're entering the era of multi-messenger astronomy, where we combine observations of light with detections of other particles and waves, like neutrinos and cosmic rays, to get a complete multi-sensory picture of the most violent events in the universe. Gravitational lensing is now being applied to these other messengers, and the results are opening up entirely new ways to see the invisible. Neutrinos are perhaps the most elusive of these messengers. They're tiny, ghost-like particles with almost no mass and no charge, and they rarely interact with anything. Trillions of them are passing through your body every second, completely unnoticed. But they are produced in enormous quantities in the most cataclysmic events, like supernova explosions or the active hearts of galaxies. Because they hardly interact, they travel in nearly straight lines from their source, unaffected by magnetic fields or dust clouds that would bend or block light. This makes them perfect messengers, but they are incredibly difficult to detect. When we do catch one, pinpointing its origin is a major challenge because their paths are so hard to trace. This is where gravitational lensing can play a surprising role. Just as it bends light, gravity also bends the paths of these massive particles, albeit to a much smaller degree. For extremely high-energy neutrinos coming from the distant universe, the gravity of a massive foreground galaxy cluster could very slightly deflect their trajectory. By understanding the mass distribution of these lenses, we could, in theory, work backwards to better triangulate the true origin of a detected neutrino, helping us to identify the monstrous engine that created it. Cosmic rays present a similar puzzle. These are not rays at all, but actually high-energy atomic nuclei, protons, and heavier elements that are accelerated to nearly the speed of light by some of the universe's most powerful accelerators, like the shockwaves of supernova or the jets from supermassive black holes. When they finally reach Earth, they smash into our atmosphere, creating a shower of secondary particles that we can detect. The problem is, because these cosmic rays are charged particles, their paths are scrambled by the magnetic fields that permeate our galaxy and intergalactic space. By the time one reaches us, it's impossible to point back to its source because its path has been twisted and turned countless times. This has been one of the great mysteries in astrophysics for over a century. Where do these ultra-high-energy cosmic rays come from? Gravitational lensing offers a potential, albeit indirect, clue. The same massive structures that lens light are also the sites of immense gravitational forces that could be powering these cosmic accelerators. By mapping the distribution of matter through gravitational lensing, we can identify the most likely hubs of extreme activity, the massive galaxy clusters and active galactic nuclei. When an ultra-high-energy cosmic ray is detected, we can cross-reference its approximate direction with our detailed lensing maps of the massive structures in that part of the sky. It's like having a map of all the major power plants in a country. If you detect a massive power surge, you know to look at the map to see which plant is the most likely source. The ultimate goal of multi-messenger astronomy is to get a complete picture of a single event from all of these different perspectives at once. Imagine a blazar, a supermassive black hole at the center of a distant galaxy, pointing its intense jet of radiation directly at Earth. This event would flood us with light across the entire spectrum, from radio waves to gamma rays. It might also generate a burst of high-energy neutrinos and accelerate atomic nuclei to become ultra-high-energy cosmic rays. If this distant blazar is perfectly positioned behind a massive gravitational lens, something extraordinary happens. The lens would magnify all of the incoming signals. We would see a magnified flare in gamma rays and visible light. We might detect a magnified number of neutrinos. Even the faint signal from cosmic rays could be statistically enhanced. This coordinated, amplified signal across multiple messengers would provide an unprecedented laboratory. By comparing the lensed light with the lensed particles, we could study the fundamental physics of the acceleration mechanisms in ways that are impossible with a single messenger. We could learn how neutrinos are produced in relation to gamma rays, or how cosmic rays are accelerated in conjunction with optical flares. The gravitational lens acts as a universal amplifier, turning up the volume on every channel at once and allowing us to hear the full symphony of a cosmic event rather than just a single instrument. This holistic view is crucial because each messenger tells a different part of the story. Light tells us about thermal processes and hot gas. Gravitational waves reveal the dynamics of massive objects moving through space-time. Neutrinos probe the hearts of nuclear reactions. Cosmic rays sample the material being accelerated and ejected. By combining them all with gravitational lensing enhancing each one, we are no longer just astronomers, we are cosmic storytellers, assembling a complete narrative of how the most energetic events in the universe truly unfold. Thankfully, you don't need a supercomputer or a space telescope to start bending light yourself. A new wave of incredibly powerful and often free educational software and online platforms has democratized this cosmic phenomenon, putting virtual gravitational lenses right at our fingertips. These tools are essential for training the next generation of astrophysicists, allowing them to experiment, visualize, and truly internalize how mass warps the fabric of reality. One standout example is the software called gravitational lensing and the apparent shape of black holes, often just called the Black Hole Lensing Simulator. This isn't a simple animation, it's a sophisticated physics engine that lets you play with the fundamental parameters of the universe. You can place a black hole of any mass onto a grid representing space-time, and then watch in real time as it distorts the background image of a galaxy or a star field. You can adjust the mass, change your viewing angle, and even watch what happens as you move the background source. It transforms an abstract equation from general relativity into an intuitive, interactive experience, making the invisible force of gravity suddenly visible and tangible. The learning power of these simulations comes from their ability to model not just perfect textbook scenarios, but the messy, complex reality of the cosmos. For instance, most platforms allow you to experiment with different mass distributions. You can start with a simple point mass, which creates the classic Einstein ring effect, and then graduate to a more realistic, extended mass like a galaxy cluster. Here, you can add dark matter halos of varying sizes and densities, and instantly see how this invisible scaffolding changes the resulting lensed images. The software can generate multiple images, giant arcs, and even time delays, providing a complete sandbox for understanding the intricate dance between light and gravity. This hands-on experimentation is crucial because it moves beyond passive learning. Instead of just being told that dark matter exists, a student can see its effect by adding it to their model and watching the lensing pattern become dramatically stronger, providing a visceral understanding of its dominant gravitational role. Beyond standalone software, massive public data archives and web-based visualization tools are opening up professional research to anyone with an internet connection. The Hubble Space Telescope's data, for instance, is freely available to the public. Platforms like the Mikulski Archive for Space Telescopes, or MAST, host these incredible datasets, and with a bit of guidance, amateur astronomers and students can download the actual images used by scientists to discover gravitational lenses. Then, using open-source image processing software like DS9, they can adjust the contrast, apply filters, and search for those telltale arcs and multiple images themselves, recreating the discovery process. This direct access to real data transforms abstract concepts into a tangible hunt, fostering a deep connection to the actual work of science and empowering a new generation of citizen scientists to potentially make their own contributions. Perhaps the most profound impact of these tools is their ability to foster intuition about the non-intuitive. General relativity is famously counterintuitive. Its predictions often defy our everyday experiences. But by interacting with a simulation where you can literally drag a black hole across a star field and watch the stars warp and stretch around it, the brain begins to build a new model of how the universe works. This is how professional researchers develop their own deep understanding, by constantly running mental simulations. Now, these digital tools provide that same mental framework for students, building the foundational intuition needed to ask the next great questions. They are the training grounds where future scientists learn to speak the language of curved spacetime, a language they will use to one day decode the universe's darkest secrets, from the nature of dark energy to the quantum foam at the edge of a singularity. But as we chart this invisible architecture and contemplate technologies that might one day harness its principles, we're inevitably faced with profound ethical and philosophical questions that reach far beyond the equations. What does it mean to fundamentally alter our perception of reality, to learn that most of the cosmos is made of stuff we cannot see or touch? For millennia, humanity's place in the universe was defined by the stars we could observe, our myths, our calendars, and our sense of scale were all built upon that visible tapestry. Gravitational lensing hasn't just added new stars to that map. It has revealed that the map itself was drawn on a foundation we never knew existed, a dark matter scaffold that holds everything together. This can be a deeply humbling realization. It displaces us from the center of things not just physically, but conceptually. We are not merely living on a planet orbiting a star in a galaxy. We are temporary residents within an immense, invisible structure whose full nature and purpose remain just beyond our grasp. This can provoke a kind of cosmic awe, but also a sense of vulnerability as we come to understand the sheer scale of forces that operate independently of our existence. This newfound knowledge also brings with it a weighty responsibility, particularly as we look toward a future where understanding these forces could lead to the ability to influence them. The history of human innovation is a story of discovering a fundamental principle, electromagnetism, nuclear forces, and then learning to harness it, often with world-altering consequences. The leap from understanding gravity to potentially manipulating it is one of the last great frontiers of physics. While it may sound like the realm of science fiction, the serious scientific investigation into the nature of gravity, propelled by discoveries from lensing, is the essential first step. The ethical imperative is to begin these conversations now, long before any such technology is feasible. If we were to ever develop a capability to interact with the fabric of space-time or the dark matter that shapes it, the power would be unimaginable. It could enable feats like the warp drives of popular imagination, but it could also become a tool of unprecedented destructive potential. The same gravitational lens that lets us see the birth of galaxies could, in a different context, be conceptualized as a weapon of cosmic scale. The international scientific community has a duty to foster transparency and open dialogue about the direction of this research, establishing ethical guardrails through global cooperation rather than isolated national competition, ensuring that such a profound understanding of the cosmos is guided by a moral framework as advanced as the science itself. Moreover, this journey of discovery forces us to confront the question of cosmic purpose, or the lack thereof. Mapping the invisible universe reveals a cosmos that operates according to elegant mathematical laws, but one that is also indifferent. The gravitational forces that so beautifully lens the light of distant quasars would just as easily tear a spaceship apart. The dark energy accelerating the expansion of the universe is doing so with no regard for the eventual fate of the galaxies and any life within them. This presents a critical choice of perspective. One can see this as a universe devoid of inherent meaning, where humanity is a fleeting accident in a vast mechanical system. Or one can see it as a universe of incredible potential, where meaning is not given but created by conscious beings who are fortunate enough to emerge within it and capable enough to decode its secrets. The act of discovery itself, the relentless human drive to understand the invisible and comprehend our origins, becomes our purpose. We are the universe's way of becoming aware of itself, and with that awareness comes the tremendous responsibility of stewardship, not just of our planet, but of the knowledge we uncover and the future we choose to build with it. This isn't just about physics. It's about shaping a future where our expanding cosmic consciousness is matched by an expanding ethical wisdom, ensuring that as we learn to see the invisible, we also learn to build a future worthy of the view. Now, the most cutting-edge research is pushing this tool into realms that sound like pure speculation, using lensing to search for objects and phenomena that have so far lived only in theory and science fiction. Among the most tantalizing targets are primordial black holes. Unlike the stellar mass or supermassive black holes formed from dying stars or galactic mergers, these would be relics from the universe's first frantic moments, potentially as small as an asteroid yet containing the mass of a mountain. If they exist in large numbers, they could solve the long-standing mystery of dark matter. The hunt is on using microlensing, surveys are monitoring millions of stars in nearby galaxies, watching for the characteristic brief brightening that would occur if one of these tiny, invisible black holes drifted in front of a distant star. Finding a population of these ancient objects would revolutionize our understanding of the universe's birth and its hidden mass. Beyond new objects, gravitational lensing is our most powerful tool for testing the very laws of physics, probing theories that attempt to go beyond Einstein's monumental work. So-called modified gravity theories, like MUND, propose that our understanding of gravity is incomplete and that on the largest scales, it behaves differently than general relativity predicts, potentially eliminating the need for dark matter altogether. These theories make very specific forecasts for how light should be bent around galaxies. By using weak lensing to create exquisitely detailed maps of the actual mass around thousands of galaxies, and comparing the observed distortion to the predictions of both standard physics and these alternative models, astronomers are performing a grand cosmic test. The data so far strongly supports the existence of dark matter, but the precision of these lensing measurements continues to tighten, either solidifying our current model or potentially revealing the subtle cracks that point toward a new physical paradigm. Perhaps the most speculative and thrilling frontier is the search for topological defects in spacetime, things like cosmic strings or even wormholes. A cosmic string is a hypothetical, infinitesimally thin crack in the fabric of the universe left over from its early, high-energy phase, possessing immense density and creating a unique gravitational lensing signature, a perfectly duplicated, identical image of a galaxy or quasar on either side of the string. Astronomers are actively scanning the sky for this perfect double, a telltale sign that the universe's underlying structure has a flaw. Wormholes, often portrayed as shortcuts through space, would also have a distinct lensing fingerprint. While often visualized as a tunnel, a traversable wormhole would have a throat that could act as a gravitational lens, but with a bizarre effect. It could create a unique pattern of multiple images, including ones that show light from the object that has traveled through the wormhole itself. Finding such a pattern would be arguably the most profound discovery in the history of science, proving that the universe is not only stranger than we imagine, but stranger than we can imagine. Ultimately, all these frontiers converge on the deepest question of all: what is the true nature of spacetime? Is it the smooth, continuous fabric described by general relativity, or does it have a graininess, a quantum foaminess when examined at the smallest possible scales? This quantum foam would be a seething sea of virtual particles and tiny wormholes popping in and out of existence. While these fluctuations are unimaginably small, their cumulative effect over the billion light-year journey of a photon could, in theory, very slightly scatter its path. By analyzing the light from distant, point-like quasars that has been strongly lensed, scientists are looking for a specific kind of blurring or speckling in the resulting images, a faint signature that the light has been jostled by the quantum texture of spacetime on its long voyage. It's a minuscule effect requiring mind-boggling precision, but it represents our first tentative attempt to use the cosmos itself as a laboratory to finally bridge the chasm between the physics of the very large and the very small. And so, this cosmic quirk predicted on a chalkboard over a century ago has blossomed into one of the most indispensable tools in our astronomical arsenal. It began as a curious validation of Einstein's genius, a slight bending of starlight during an eclipse. Today, it is the master key unlocking the universe's darkest vaults, transforming the invisible into a detailed, three-dimensional map. From the ghostly halos of dark matter that scaffold the cosmos to the faint, magnified glow of the very first galaxies, gravitational lensing has handed us a new set of eyes. It allows us to witness the universe's most violent collisions through the echo of gravitational waves, to hunt for rogue planets wandering the void, and to test the laws of physics under conditions so extreme they defy earthly imagination. This is more than just a tool for observation. It is a paradigm shift in our cosmic perspective. We are no longer limited to the light that happens to fall directly upon us. We have learned to read the distortions, to decipher the wrinkles in spacetime itself, and in doing so, we have uncovered a universe that is vastly larger, stranger, and more magnificent than we ever dreamed. The mysteries of dark energy and the ultimate fate of the cosmos, the nature of spacetime at the quantum level, the search for life on distant exoplanets, these are no longer questions for pure speculation. They are puzzles we are actively solving, with gravitational lensing providing many of the crucial pieces. As we look to the future, the potential applications stretch beyond pure science into the realm of tomorrow's technology. The same principles that allow a galaxy cluster to act as a natural telescope might one day enable a network of gravitational lenses to serve as an interstellar communications system, turning the entire galaxy into a connected community. Understanding the dark matter web could provide the most stable gravitational pathways for future generations embarking on voyages between stars. We are moving from being passive observers of the cosmos to active participants, learning its rules and perhaps one day learning to navigate its currents. The greatest lesson gravitational lensing teaches us is one of humility and wonder. It reveals that what we see is only a tiny fraction of what is real. The true substance of the universe, the forces that drive its evolution and dictate its structure, are hidden in plain sight, waiting for us to develop the cleverness to perceive them. So the next time you look up at the night sky, remember that you are not just looking at points of light. You are looking at a lens, a magnifying glass crafted by gravity itself, warping our view to reveal the profound and invisible truths of our existence. Stay curious about the dark, the distant, and the unseen, for that is where the next great revolution in understanding awaits.